Thank you for the introduction. And first of all, I'd like to thank the organizer for giving me the opportunity to present here today this work on the search for dark matter annihilation signals with the S Inner Galaxy Survey that I've done in collaboration with Emmanuel Moulin and Denis Malishev, and I'm presenting on behalf of the S collaboration. So just a brief outline. First, I'm gonna introduce the talk, something about WIMPs and indirect dark matter searching gamma rays. That we're gonna see what is the inner galaxy survey performed by S. We're gonna see the S data analysis and the computation of the upper limits and the annihilation cross-section of the WIMPs, and I'm gonna run through the conclusions. So for this talk, so we are searching for WIMPs, assuming therefore the cold dark matter paradigm. And as I said, we are focusing on weakly interactive massive particles that you can see highlighted on the scale of masses of possible candidates for dark matter. And I'm just going to recap that when we assume that are created, the WIMPs are created thermally in the early universe, we can compute the annihilation cross-section expected for thermal WIMPs. And so we know that WIMPs can self-annihilate and produce standard model particles in the final states. You can see from the sketch what are some of the possibilities of the final states of two dark matter WIMP particles annihilating. And this, especially gamma rays in the final states of two WIMP annihilating, can be eventually detected by satellites and ground-based experiments. So you can see on the sketch on the right, just to summarize some of the possible detection technique that we have for detecting gamma rays from annihilating dark matter. Like so we have satellites like Fermi-LAT, then we have water Cherenkov detectors as OAK, and AICTs as in this talk we are going to focus on S because I'm showing you results obtained with S data. So for so as I said, WIMPs can self-annihilate, and gamma rays in the final states can be eventually detected by H.E.S.S. So when we assume the annihilation process takes place almost at rest, we know that the smoking gun signature for dark matter spectra is a very distinct energy cutoff, close to the dark matter particle mass. You can see the spectra for dark matter annihilating in the plot on the right of the slide. So this is for fixed dark matter mass of the dark matter particle, and for different annihilation channels that we considered in our work. So you can see the very distinct energy cutoff at the dark matter particle. And so we know the gamma ray flux expected from dark matter annihilation, which is given by the equation in the slide. And we have the particle physics factor, which is highlighted here by the blue shape. And then we also have the astrophysical factor in the expected gamma ray flux. The astrophysical factor, which is the JFactor, as already introduced Michele in the previous talk. And on the right of the slide, you can see a plot showing you a JFactor when we assume an ANASTO profile for the galactic center region. So this map is given in galactic coordinates, so longitude and latitude, and you can see the values of the JFactor, so computed from this equation, in the galactic center region. So we know that we need a model for the density profile, the JFactor, and we also have a dependence on how the dark matter halo is modeled. So then I'm gonna show you what are the possible targets. We have galaxy satellites of the Milky Way, in which we have a low astrophysical background, and many of them are within the 100 kiloparsec from the galactic center region. Then we have dark matter subhalos in the Milky Way halo, in which the signal is even lower than the galactic center region, but we have no other wavelength counterpart and no conventional astrophysical background. And then we have the galactic center region and the inner galactic halo, which are the targets on which I'm focusing on this talk. These are the possible brightest source of dark matter annihilation signals because they are really close to us. But we have the uncertainty on how the dark matter profile is modeled, and we also have an high astrophysical background source confusion and a galactic diffuse background that has to be treated when analyzing data taken from this region. So what is the Inner Galaxy Survey? Is the first ever conducted very high energy gamma ray survey of the galactic center region, with the aim to provide unprecedented sensitivity to also dark matter signals in the galactic center region. So this is a plot of the observation of the inner galaxy survey performed with H.E.S.S. So the dataset that we are considering has been taken between 2014 and 2020, and the plot shows the exposure map with the H.E.S.S pointing positions. So you see that we have a good exposure, especially in the inner galactic halo, up to 300 hours with our pointing positions. And for the dark matter search, we define 25 regions of interest, which are the 0.1 degree with open rings, shown as purple rings in the plot. And you see the white shaded areas. These are the exclusion regions that we applied in our analysis to avoid gamma ray contamination from the background that we know in the galactic center region in our ROIs for the search of dark matter. So how do we measure background, and how do we build our distribution of events? So we have the 25 rings of our ROI. We apply a reflected background method, meaning that we build the off region as to be symmetric to the on region with respect to the pointing position. So we have same field of view and acceptance. And the excluded regions are cut symmetrically in on and off region. So we maintain same solid angle size, and we cut overlapping areas and areas where off is closer to the galactic center than the on region. So the dark matter signal in the on region is always higher than in the off region. And we repeat this procedure for all the 25 ROIs and over all the runs taken for our dataset. So you see in the plot that we have the two ROI 14 and 18. These are two examples of our own regions, and then we reflect them with respect to two pointing position to obtain basically the off regions. The color scale is just basically the JFactor values for again the inasto profile, which is shown inside our ROIs to show you that we always have more expected dark matter signal in the on region than in the off region. So to build our analysis, we use a likelihood analysis method, and we build test statistics. So we use 2D bin Poisson likelihood function, which is given by the equation in the slide, and we compute a total likelihood function by considering a product over spatial and spectral bins, so over the ROIs and over the energy bins. So we have in the function the number of measured events in spatial on and off regions given by n on and n off, and S and NB are the expected total number of events in the spatial on region, and then we have also them in the off region given by ns prime and alpha nb, and alpha is the ratio between the angular size of on and off regions, and these terms are plugged into the likelihood function, and then we run our analysis. So we also included the systematic uncertainty. We did an extensive study on the systematic uncertainty via a nuisance parameter. We fixed a value of 1% in sigma beta, which is given here, and it is given also in the equation, the sigma beta. And then we determine a value of beta via conditional maximization. So we compute it for each energy and spatial bins. So when we have no significant excess in our field of view, we derive 95% confidence level upper limits on the annihilation cross-section, in this case as a free parameter, from a log likelihood ratio test statistics. And we also computed expected limits and containment bands by using independent Poisson realization of the on and off measurements. And so these are the results. So these are our limits obtained from this work. So we have these are S upper limits, the observed one as solid black line, the expected one computed from the post-normalization as the black dashed line, and then we have the containment bands. These are obtained for our entire data set. For only these are shown just for WW annihilation channel and assuming the Enasto profile. And in this limit, we have the systematic uncertainty included. And we compare them with other limits. So these are the most constraining limits in the TeV energy range. So we have our limits are the black, again, solid line. We compare them with the previous S upper limits and limits from our instrument. So we can see that here we can challenge, we start to get close to the thermal relic density. So my conclusion is that the H.E.S. campaign has been very fruitful and we have a lot of data to analyze. We computed upper limits on the annihilation cross-section, also including systematic uncertainty. So with the unprecedented H.E.S. dataset, we obtained the strongest constraints obtained in the TeV mass range. And in other annihilation channels, we also can probe the thermal relic scale. And so to conclude that the H.E.S. is one of the legacy of the H.E.S. collaboration, and it also paves the ways for the future observation with CTA. Thank you.